Okay, so before the break, we talked about ridge regression and we got into talking about the lasso. Okay, so we said that the lasso regression may be more suitable for variable selection, although, we said that if your ridge regression coefficients are getting close to zero, that might be sufficient enough for you to do variable selection. You may not actually need them to equal zero exactly. And we talked about uh, that a little bit in terms of the context of predictor selection in general. But nonetheless, we say that Lasso will yield the sparse model involving only the subset of variables. Well, let's look at this a little bit here in terms of how that works. These are similar plots as we saw earlier when we looked at ridge regression. So here we have the value of lambda. Okay, there's the value of lambda. And here's the value of lambda at zero. So ordinary least squares. There's our least squares regression. Okay, so right over here. So again, if you're looking at this plot and someone says to you, they say, well, what are the predictor values for least squares? Well, the predictor values for least squares are when lambda equals zero. Because whether you're using ridge or you're using lasso, if this is equal to zero, that penalty term goes away. Right? Remember in the equations we just looked at, more familiar when we looked at ridge regression, but it's the same idea with lasso. The only difference with the lasso is in terms of the penalty, right? But you still have this before the summation. This still exists before the summation. So this here sets to zero. You're not adding any penalty term, regardless of what comes after this. So, whether this is the ridge or the lasso idea, this setting to zero eliminates the penalty. So lambda equals zero, there are the values of your coefficients right here. So what happens as lambda increases? Well, as lambda increases, what should happen in line with what we talked about with ridge is we should have shrinkage, right? We should have shrinkage. We should have this idea of regularization, right? They're going to kind of regulate the model a little bit. So what happens? Well, we should start to see these things go towards zero. And isn't it interesting, right? When you look at this plot, wow, like a whole bunch of things seem to be happening in here. It's not quite as simple as, just getting them towards zero. And that's what I said in the first part of the lecture. I said, you choose a value for the tuning parameter. It's not like things are just going to drop down to zero and you're going to have a final decision on the model. The selection of this tuning parameter is pretty critical when you really think about it. I mean, look at this. Look at the range of the tuning parameter. Look at the behavior, right? Think of this as behavior of the different variables in the regression. I mean, look at this one. This one here at a tuning parameter of 50 hardly changes. Okay, hardly changes. Whereas this one up here, well, maybe it dropped down a little bit more. This one here hardly changed. You get to 200 over here. Well, what's going on? This one's getting increasing in value. Now, increasing in value, we mean towards zero because it's a negative. Start off in the negative. So the increase is towards zero. It's a decrease in magnitude, which is what we would expect to happen, right? This should start to go towards zero. But look at the others, right? Well, there's that blue one again, or the dotted blue. We see that there's actually an increase. And this one actually takes, to make it even more complicated, it takes a different form. It doesn't even increase and then decrease towards zero. It actually takes a step here and kind of plateaus here a little bit for certain values of lambda. And then suddenly decides, all right, that's it. I'm going towards zero. I mean, this one is like quite decisive. When this one decided to go towards zero, it wasn't fooling around. It just said, I'm going towards zero now. Bang, drop like that. But you notice that some of these coefficients went to zero before others. Okay, and that's the key, is that this one here, which one was that? That was the income variable. This one here got to zero over here. These two kind of merged towards 0 over here, and it's the rating variable that's the interesting one, right? That one kind of did this, and that was the last to go towards 0. So you can see why the authors are talking about this potentially being useful for predictor selection, variable selection, because it's going to set them to 0, and you can choose different values of lambda to kind of see what's going on at different values. Now, the question remains how to choose this, right? We still haven't answered that question. Okay, we still haven't answered that question, how to choose this, because it could seem rather arbitrary, which is why I said before the break, I said you never want to hear someone doing a lasso or a ridge regression just announcing the coefficients. Right? That would not be a good idea for you to just take that in and to kind of say, well, they said, if someone says, I did a lasso regression and here are my coefficients, there's more to the story than that. What were the choices of lambda available? And how did lambda compare across the broad spectrum? And how did the author, presenter, what have you, choose that particular value of lambda? Okay, they should be choosing that value of lambda based on some criteria like cross-validation that we'll talk about briefly for selecting that value. But this, as it's mentioned in the book, that's a critical thing, as you can see. It's very critical. If these all had the same behavior regardless of the choice of lambda, then it's not so critical, but we can see that changing lambda has quite a big of an influence here. Now, if we turn the plot around, like we had in the ridge regression, well, we can do the norm thing again, right? So we start off with OLS, lasso, coefficients the same as the least squares. If this number is the same as this, you get a coefficient of 1, right? If those two are the same, you're going to get a coefficient of 1. So this is where we start off with the ridge as well. But what happens as the coefficient vector for lasso, right, gets smaller, right? The coefficient vector gets smaller. So this norm, this distance, gets smaller. Well, it gets smaller and smaller and smaller until what? These things are being set to 0. So you're seeing this is doing basically the opposite of what this plot is doing. We're starting here in this plot, we're moving this way. It's the same idea as what we looked at in our regression or our ridge plots. And you can see that we eventually get to where we've got everything at 0 over here. Right? Eventually it always goes to 0. So that's why we're getting this ratio equal to 0. Because at this point, well, everything's set to 0 for the lasso. So, this one is staying the same. This one isn't changing as we move from this side to this side. This one is just set at 0. So you're going to get a value of 0. You see what's going on in that plot. So you can think of it this way, right? You can think of it this way. This one here was the last one to go towards 0 over here. That's that, which one is again? The rating, the last one to go towards 0. So maybe when you look at that, that rating variable, right? Maybe that rating variable might be maybe a pretty important variable relative to the set. Because even as you increase lambda, this one kind of stays in the model, right? This one stays in the model. As the distances get smaller, so your coefficient vector heads towards 0, this is the last one. So maybe there's something about that rating variable. And there's nothing wrong with choosing different types of models to examine the rating variable. You're examining the rating variable in the context of these other variables, but there's nothing wrong with triangulating models. You might try a regularization technique. You might try a hierarchical regression technique to kind of see if you get some convergence. There's nothing wrong with doing those things, as long as you're honest about what you're doing. You don't want to pretend like the model that you chose or the procedure that you ran is the only one you ran. You want to be honest about all procedures that you ran in helping you decide, maybe rating is more important in some contexts. Okay, so you want to look at all those things. Okay, so we see basically the same idea here for the lasso as we saw for the ridge. The advantage of the lasso, again, is this describes everything we just talked about. The advantage of the lasso, again, is that you may be able to be used for variable selection, right? Because of this idea that it goes to 0, right? So with the comparison to ridge down here, ridge will always include all of the variables in the model, although the magnitude will depend on the value of lambda. So you might prefer the lasso to ridge, and there's not even anything wrong with comparing both models in the same data set. I mean, I hope one thing that's coming from this a little bit from this discussion is that there's a lot of stuff that goes into model value. There's a lot of things that go into how to assess the importance of predictors, and regularization is one technique that may be useful for that purpose. But remember, this is looking at it from a purely statistical point of view, right? By what I mean by a purely statistical point of view is that nowhere in here are we actually talking about these variables. We're just naming them income, limit, rating, and student. So to select a model based on only the behavior of a lasso regression or a ridge regression, probably going to be a mistake, right? It's probably going to be a mistake to only look at what the statistics are reporting. You have to merge that a little bit with practical considerations as well. And as we're going to see, even if the cross-validation error, right, ends up being the absolute lowest for one of these models, doesn't necessarily mean that's going to be the final verdict model. It means it's going to be the final model from a statistical point of view, but you also have to look at your predictors, right? How reliable are these predictors? Were these measured well? How honest are people about their incomes? Where are you getting this information for income? Are you asking people what their income is? Are you getting it from a reliable source? What is their rating? What's their credit limit? Things like that. And I mean, this model is probably relatively simple in that capacity. You know, it's probably like getting their credit limit and their rating and things like that is probably going to not make that much of a difference in terms of the usability of these predictors. But again, you can imagine a situation where one predictor, maybe it's just not worth including it, or it's too expensive to recruit, or, you know, to use kind of like a silly example, if you have to fly out to outer space to analyze the behavior of somebody in microgravity, and that ends up being a really good predictor of depression rate, well, that's just not feasible, right? Even though, what if it's a perfect predictor, right? What if it's like a really, really good predictor? Well, flying someone out into space and observing their behavior in microgravity is not doable. So maybe you should mention that that has a good statistical quality, but from a scientific point of view, from a usability point of view, in trying to predict the depression rate of your next client walking into your office, boy, that's just not going to work, because you don't have time to send somebody out into outer space, and it's really, really expensive even if you had the time. Okay, so extreme example, but you get the idea. Model selection from a scientific point of view has to incorporate more than these statistical indicators. Okay, well, another formulation of ridge and lasso, really, really high marks for this one, as you can see from the smiley face. Okay, this is like, wow. Because remember when we started off the ridge, and remember when I said this doesn't really tell you what ridge does completely, right? Because it said you select a value of lambda, you minimize the criterion of the residual sums of squares subject to a penalty, and it experiences shrinkage. Well, it didn't really tell you what ridge was doing and what lasso was doing. This tells you a little bit more in this formulation. Okay, there's a lot of equal formulations in statistics. You formulate a problem one way, you can formulate it in an equivalent manner in another way. And this way is really nice because look what this does. Let's start off with the ridge. They put the lasso first. Let's start off with the ridge. We know that we want to minimize that sum of squared quantity, right? We want to minimize that. So this is this is good. This is like ordinary least squares regression. You're minimizing that quantity. You're minimizing the residual sums of squares. But subject to this constraint. Okay, subject to this constraint. So what is this constraint? Well, we know that ridge deals with squared values. And what this is saying is that this has to be minimized subject to the sum of squared coefficients has to be less than or equal to some preset level of S. Now remember I mentioned S, right? I mentioned S earlier, and that we're going to return to what that is. Well, for a given S, there's a given value of lambda. Okay? So if you minimize according to some value S, that has an implication, using a double line and arrow say implies, the lambda implies an S value. And what this formulation here does is it tells you how these coefficients are being obtained, which to me, this is the presentation of ridge and lasso that's most important in the chapters. You understand how the coefficients are being obtained. They don't tell you at the beginning of the chapter when we surveyed it how those coefficients are being obtained. They just said you obtain them and you can modify the value for lambda. But this tells you the exact minimization that's taking place. And really, I mean, they amount to the same thing because the other stuff, because of this implication of lambda implies S, the stuff that we saw on the first page amounts to the same thing as this. It's in a different formulation. I mean, I'm not sure if there's another word for it. It's in a different presentation, but it's more meaningful, and we'll see in the next page in a second. So minimize this. Subject to the sum of those squared B values has to be less than or equal to some S. And again, this is a constraint. Okay, this is a constraint on the problem. That says constraint. That's not very well written, but that says constraint. Okay, and what's the constraint? The setting of S. What's the setting of S? Has an implication for lambda. So really what we did in the first page of the ridge regression, when we said we're minimizing RSS, and then we said you can choose any values you want greater or equal to 0 for lambda, we're actually doing a minimization process by choosing that value of lambda, subject to this condition here in ridge and subject to this condition here in the lasso. Notice we have absolute values, and here we have squares. Okay, the norms are different, those the L1 and the L2. But you see what's going on in those procedures. So really interesting way of formulating the problem, and I would say is the better way. Now let's look at what this does when we look at a plot. We're going to look at a plot in a second, and in that plot, we're going to look at lasso coefficients, and we're going to look at ridge regression estimates. But I want to just talk about this briefly, and I'll compare it to the plot in a second. We're going to have P is equal to 2. So we're going to have two variables, and we're going to say that the lasso coefficient estimates have the smallest RSS out of all points that lie within the diamond defined by this criteria here. Smaller or equal to S, our constraint. So remember we said we're going to choose a value of S, set it as a constraint. Well, we're going to look here in a second that we're going to impose that constraint. We're going to put it into a plot so you can see where the constrained areas are. That value for the lasso has this constraint. B1 plus B2 is smaller than S, smaller or equal to S. Okay, the absolute value, the absolute value. Look at what it does for ridge. That sum squared has to be smaller or equal to S. So when you perform the lasso, as we're going to see in a second, we're trying to find a set of coefficients that lead to the smallest SS, right? We're minimizing RSS. We're minimizing RSS just like we would in least squares regression, but subject to the constraint that there's a budget S for how large the sum here can be. Notice that it's a budget, right? That's a budget right there. So minimize SS, or RSS rather, minimize RSS subject to this condition. Get the smallest RSS, that's what I mean by minimize, right? Get it small. Say, hey, I'm going to fit a regression equation. What do you want to do? I want to minimize RSS. But do you want to do it unconditionally? No. You don't want to do it unconditionally. You want to do it subject to a constraint that for Lasso, the sum of those absolute values is smaller or equal to S. That's the idea. Ridge regression is the same idea, only you're squaring the b's. So that's why the book is talking about this as a budget. The budget S for how large this can be. So when S is extremely large, okay, that's what they're talking about here. When it's extremely large, the budget's not very restrictive. And so the coefficient estimates can be large. Okay, think about that for a second. So if you make that budget really large, well, it's not very restrictive and the coefficient estimates can be large. Here's a really, really important point here. If S is large enough that the least squares solution falls within the budget, then that formulation we just looked at will simply leave the least squares solution. So we're looking at the graph in a second. You select a large S. Well, it's not quite a budget, right? It's not that big of a budget, and the least square solution might actually fall into that budget. So let's look. That's kind of the analogous statement is saying, hey, if you want lambda to be like, if you want the least square solution, well, just adjust your lambda to equal 0. Right? Just adjust your lambda to equal 0 and you'll have the least square solution. And that's what we talked about earlier. You set your lambda equal to 0, there's your least squares. Are you doing ridge regression with lambda equal to 0? With lambda equal to 0, yeah, you can say you're doing ridge regression. You're only setting it equal to 0 though. Okay, so when you look back at our formulation, the first formulation that we looked at earlier in the lecture, the first part, when we said lambda is equal to 0, you're just minimizing RSS. Are you doing ridge regression? Yes, you just set lambda equal to 0. So you can see that ordinary least squares can be considered a special case of ridge and the lasso for when lambda is equal to 0. We now have a bigger hierarchy in the model, right? We're talking about ordinary least squares regression, but you can look at, in this context, the ridge and the lasso, and you can look at OLS as kind of like a special case of these, where lambdas are equal to 0. Okay. Now, yeah, this part you can read over. It's not essential, but there is a connection between the lasso ridge and best subset. So let's look at this in terms of the plot that we were just talking about, in terms of that budget. Well, here are contour plots. So there's our estimated vector right here on B1 and B2. This here is our least squares estimates, what you see right here. Now, the residual sums of squares is going to be the same for each particular ellipse. Okay, so the residual sums of squares is going to be the same for each particular ellipse. And it's going to change on this one, but it's still going to be the same for any position on the ellipse. The essential point of ridge versus the lasso, right, is why does lasso lead to 0? Why does lasso lead some coefficients equal to 0? Well, look at the shapes of those norms. Okay, so we have the L2 norm and we have the L1 norm. This is L2 and this is L1. This is the area of the constraint. This is the area of the constraint that we're setting. So there's a difference between the L2 and the L1 here. The L2 norm happens to have this type of constraint boundary. It's round. Okay? It happens to have this type of constraint boundary for the shape of it. The L1 has a diamond shape right over here. So what this means is that when we move outward over here and our residual sums of squares gets larger, at some point we are going to do variable selection with the lasso that doesn't exist with the ridge. Now, why are we going to do variable selection with the lasso? We're going to do variable selection with the lasso because if you get to this point here, notice that B1 is equal to 0, right? As soon as that residual sums of squares touches the first value, right? The first value. So I'm highlighting here, this is the first point at which the ellipse contacts the constraint region. That's the constraint region, right? Defined by your lasso and your ridge. That's the first point. So we can see that in the lasso, the first point at which it contacts over here ends up being a jagged edge, right? It ends up being an edge, which means that at that edge, B1 is equal to 0. B2 is equal to whatever it is. But this is the sense where you're doing variable selection with the lasso, because then you can say, oh, B1's out. Forget about B1. It's equal to 0. Or you can just say, well, B1's equal to 0. B2 is not. I'm going to do variable selection, and I'm going to throw out B1. The lasso assumes you're going to do that. That's why it's talking about variable selection. So look here in terms of the ridge. In terms of the ridge, we don't have that jagged edge. So we see that along that contour of the ellipse, the RSS, you're getting still a value here for B1 and B2. So if you look here, the contours of the error and constraint functions for the lasso and the ridge, this is what this is describing. The solid blue areas are the constraint regions. Those are those exact regions that we just talked about on the previous page using S. This sum has to be smaller than S, and for the ridge, smaller than S. Well, the red ellipses are the contours of the RSS. So remember, along these contours, we'll give the same values for each ellipse. It's a really, really nice way of kind of demonstrating why, that all of this demonstrates why lasso will generate coefficients equal to 0, where ridge won't unless ridge goes to infinity. But you can see here what's going. And I mean, really, what does it come down to? I mean, what's the reason? So, someone asks you, they say, well, why does lasso perform variable selection and the ridge doesn't? Why does lasso set equal to 0 and the ridge doesn't? It really comes down to this, the norm. Because these norms, for reasons that we can show this if we had more time as to how this works in generating this particular shape, this norm implies that shape. This norm implies that shape over there. So when we talk about the L1 and the L2, this is the reason. why one does that, in quotes, variable selection, whereas the other one doesn't. They have different norms. It all comes down to the norm and the shapes that they assume. So that's how that works over there. So if S is sufficiently large, okay, if S is sufficiently large, right, S goes up, lambda goes down. So notice that lambda going down is exactly equivalent to the graphs we looked at earlier. Remember when we said those graphs, we said lambda is equal to 0. What do you get? Least squares. Right? When lambda is equal to 0, we said those are your least squares estimate. We put it right on the graph. It wasn't on the graph, I highlighted it, right? Remember, I just put that down there and said, those are your least squares. Now let's make lambda increase from 0 and observe the behavior of the coefficients based on the ridge regression. So this is the opposite. S increases, lambda decreases. So this should mean that as S increases, right, as S increases, gets higher and higher in value, what should happen? What should happen? Eventually, the least squares estimates should be encompassed in the constraint area. Okay, I'm going to repeat that. As S increases, eventually the least squares estimates should fall in, right? They should fall in to that criteria, right? To that constraint criteria, into the constraint region, for the same reason that as lambda decreases, we eventually get least squares. So imagine if I took this and I said, well, let's relax this a little bit, this criteria, smaller than S. Let's let S be really, really big, right? Let's let S be very large. Well, eventually you're going to have it fall into the least squares criteria and over here as well. Okay. I hope that makes sense in terms of what that S and what that lambda is doing, because now we better appreciate what S and lambda are doing. I mean, we better appreciate what lambda is doing from the outset, is that, you know, the selection of lambda is going to vary the behavior of the coefficients, but we can also see why setting lambda equal to 0 or setting S very, very large will just encompass those least squares estimates, because it'll just envelope them. What's the advantage of doing ridge or lasso? Meaning, you know, again, if you're to put it into a summary statement, what does ridge and lasso do, really? Right? What is ridge and lasso, what do? They set a stricter boundary on S. Right? They set a stricter boundary on S, smaller or equal to a particular S. They set a new budget on S. When you set the budget on S, right? When you set the budget on S, well, you leave the least squares estimates behind. They're gone. They're out there. You're now reducing that space so that only things that fall over here are going to be allowable for the lasso or ridge solution. Okay? Increase S. This will eventually fall in, right? Increase S. It eventually falls in. Increase the S over here. Eventually it falls in. Decrease it. Decrease your lambda. Increase S. Now you're talking ridge and lasso solutions. And the variable selection happens at the ridge, happens at the corner over here because of the shape of the norm, the L1. This doesn't have that shape, so you don't have that effect going on. So there it is in terms of the lasso versus ridge and how that, why the lasso is doing model selection. But again, this idea here with this use of the S is really, really good, because this tells you what's going on, right? And again, why it got the smiley faces, it tells you what's going on, whereas on the first page, Just the use of lambda doesn't tell you. This tells you the minimization subject to a constraint. It tells you what's going on, and this exemplifies it by looking at what shapes are produced by the L1 and the L2. Okay. Okay. So this is all the same stuff that we've just been talking about. Comparing the lasso and the ridge. Again, they stress this idea of it being a major advantage over ridge. They're saying that, well, the lasso performs variable selection, right? And I talked about that earlier. You can temper that a little bit. You temper it. And, they look at an example here where the lasso and the ridge, they result in almost identical biases. The variance of the ridge is slightly lower than the variance of the lasso. So, but they're pretty much the same. So really, I mean, the idea of variable selection, saying it's more interpretable model, only involves a subset of the predictors. Well, you can have a coefficient close to 0 and you can throw it out yourself. Right? You don't need the lasso to set it to 0. If your coefficient is 0.000003, you're going to get rid of it anyways, even if the lasso doesn't set it equal to 0. So I'm saying, in terms of what they're talking about here, in terms of it being a major advantage, I'm not quite sure it'd be a major advantage, but you should know that the lasso can perform that variable selection, whereas ridge doesn't. But understand what we mean by variable selection in that context. Okay, it's setting them to 0. So we say that the lasso implicitly assumes that a number of the coefficients truly equals 0, right? That's variable selection. Okay. Not surprising that the ridge outperforms the lasso in terms of prediction error in the setting. Well, the ridge isn't going to set them to equal to 0. Only as lambda goes towards infinity are they going to be set to equal to 0. So when you think about it, imagine if you do a ridge and you do a lasso. There's x2, x3 for a very simple model. Ridge keeps them all in. Your r squared is whatever it's equal to, but it's incorporating all the predictors. What do we know as we add predictors to a model? As we add predictors, r squared increases. Unless you're using like an adjusted r squared, something like that, that'd probably be a good idea so that you're not inflating r squared. Maybe this is hardly doing anything, yet r squared increases. If you do a lasso on this, gets rid of this, right? Says x3 is set to 0. Well, then you don't incorporate that in your variance estimate for r squared. You're only using x1 and x2. So keep that in mind as well when you come across ridge and lasso, and if ever you perform it, that you have to be aware of all those things. Okay, so more stuff here, not required reading. Talk a little bit about Bayesian relations to this. Just want to talk briefly about the tuning parameter, and then we'll be pretty much done with this chapter. So, the big question we talked about earlier is how to choose the value for lambda, right? How to choose the value for lambda. Well, I kind of hinted at the idea, I was kind of giving it away as we went along. We said the cross-validation error for each value of lambda, as we talked about chapter 5, that's a really good idea, right? So then you can select the tuning parameter for which the cross-validation error is smallest, right, is a minimum. Get it? So the cross-validation error is the smallest. Cross-validation is the idea of applying the model to new data, right? You're applying the model to new data, so that's the error you'd like to get low. Okay, analogous to if you're a therapist and you have a really good theory, well, apply it to some new people and see how it works. So in this sense, you're choosing the value of lambda that minimizes that. Again, realize optimization problems, right? We're minimizing, we're maximizing, usually subject to some constraints. And that theme is going to come back when we talk about the principal components analysis pretty soon, and most likely into next week. So cross-validation error here, value of lambda here. We notice that the cross-validation is the smallest right here. Now, if you look at the value of lambda here for the coefficients, those are the betas, standardized coefficients, there's the values that you would select corresponding to that particular lambda that has the lowest cross-validation error. So in a sense, we've kind of answered that question we started off with. You know, when somebody says to you, they say, well, I did a lasso or a ridge, and here are my coefficients. Your question is, how did you choose those coefficients? And, you know, if the response is, well, they just happen to come out with the program, right? I don't know. I just got coefficients for the program, almost like I did in ordinary least squares, right? If that's the answer, concern, right? You're concerned about that because that means that the person doing the lasso or the ridge may not be aware that they actually had a say into what that tuning parameter is. Because remember, this tuning parameter is a decision you're making, and you're varying the value of the tuning parameter and observing the behavior of the coefficients. Right? You're observing the behavior of the coefficients. So there should be some idea of cross-validation involved where you can minimize that error, and that helps you decide where the value of lambda is. And then you can observe where they happen to fall in terms of the betas, right? So here are the, you know, you can say here are the optimized betas. The optimized betas, and then someone says optimized relative to what? Well, optimized relative to this criteria for the cross-validation. Okay. Okay, so that's it for that. Dimension reduction techniques. I'm going to skip to chapter 10 because without understanding dimension reduction techniques, this section won't make sense. So we're going to go right to chapter 10, and we are officially into principal components analysis. And we're almost there. Nope, one more. Now, we've talked about principal components analysis already in terms of what it is a little bit. And we talked about it in terms of Eigen Analysis. Okay. So the first thing to realize about principal components analysis is it can be obtained. You can obtain principal components through Eigen Analysis. You can obtain it through other means as well, but here's that fundamental equation that we've already talked about. You have x, which is a vector. You have x, which is a vector, and associated with that vector is going to be an eigenvalue. Okay? It's going to be an eigenvalue. So we have one side of the equation where we have some matrix with a vector is equal to that vector, right? Those are the same vectors, with an associated lambda. I'm going to give the very intuitive idea of what this transformation looks like, because it is a transformation. And I'm going to take the pumpkin and explain how Eigen Analysis is going to be related to this components idea. So there's the pumpkin right there. That, something like that. So I'm going to take this pumpkin, and in this pumpkin are a whole bunch of vectors. There are a whole bunch of vectors in the pumpkin because this pumpkin is graphed on a grid, right? It's graphed on a grid of values, right? Where you might have like 0 right over here, but there's a whole grid of values, and you have a whole bunch of vectors in there. Now I'm going to issue a transformation, okay, on the pumpkin. I'm going to transform the pumpkin. So I'm going to transform it, and the transformation is going to look, say, something like this. Now this is just by analogy, it's not perfect, but it's really going to help in terms of having an understanding of what is going on in components analysis and what these eigenvalues and eigenvectors are about. So there's my transformation. this way. I kind of squished it a little bit too. I transformed, I might have like squished it in here a little bit like that. So I issued some kind of a transformation on it. The exact nature of that transformation we'll talk about as we go on, but it's been transformed. When I transformed it, most of these vectors in here stay on their span. They don't get pushed off their span. So they stay where they are. They weren't moved around. However, there are some vectors that stay on their, oops, that is too big. There are some vectors that stay on their span, but get changed in terms of magnitude. So this vector here, I'm putting in red now, was here all along. I did the transformation, and here it is right here. It's still here. But due to the transformation t, this vector is now going to be elongated. It's now going to be elongated by a value equal to lambda. Now, this is not the same lambda as the tuning parameter. This is the lambda here in terms of the Eigen analysis. But it's going to be elongated by the lambda. Now, technically speaking, this vector, right, this vector is x. This vector x can be elongated, it can be shortened, it can go in the negative direction. I mean, mathematically, that can happen. We're going to see in PCA that eigenvalue is going to be a positive quantity, because it's going to be a positive quantity because we're going to see that this eigenvalue is expressing the variance of the component, but it's going to change that length in terms of the magnitude of that vector. Okay. So it's going to, typically for the principal component, it's going to take that vector and it's going to multiply it by the value of the eigenvector. And then this new vector here is going to be called a principal component. It's going to be called a principal component because it was simply changed by a value of the eigenvalue. That's what's going to make it so special. The other vectors that get knocked off their spans and move around and stuff like that, those are not principal component vectors. That is a principal component vectors because in a sense it was principal, right? It's like you can transform the system, but this vector says I'm not budging. I'm only going to change my length in terms of that magnitude as determined by lambda. Okay, that's an idea of what these principal components are, and what these eigenvalues and eigenvectors are. Now, there's going to be another one here, let's say over here. That's going to be component number 2. So this is number 1, and this is number 2. This component 2 is at a right angle to the first component. Okay, it's a right angle to the first component. So what we're going to try to do is, and that component also is going to be associated with an eigenvalue. So what we're going to do is we're going to conceptualize this as being a transformation of this information to this information. It's a transformation. That's what's key to this. Okay, cannot emphasize this enough. That principal components analysis, PCA, is a transformation. And in the transformation, we're trying to see what vectors are, in a sense, fundamental to that transformation. What vectors are fundamental to that transformation in the sense that they only undergo change by multiplication by this special value called an eigenvalue. Okay, that's an eigenvalue. This vector is called an eigenvector, but that's not very well done. That's an eigenvector. So associated with each eigenvector is going to be an eigenvalue, where the eigenvalue is describing that magnitude change. Now you can see why I chose the pumpkin example this way, because the transformation takes place where the pumpkin changes in terms of shape like this. And if you were to describe the shape of the pumpkin, which vector in here is giving you kind of like the most bang for your buck, is describing most of the information. Most of the information is being accounted for by eigenvector number 1. And the fact that this was multiplied by an eigenvalue, right? So this carries even more importance, right? You know, it was over here, it wasn't that important. The transformation happened. Wow, this is really, really important, because if you know this eigenvector, you know a lot about this system. You know a lot about the information. You know a lot about the transformation. This is the idea of eigenanalysis, which these eigenvectors, the elements of this eigenvector, okay, the elements of the eigenvector are going to be loadings on the component. Okay, these are going to be elements of the eigenvector, and then we're going to produce a component out of this. But this is the big idea, and the key is a transformation. So in all of this stuff about transformation, what we first need to realize that though we can get the principal components in different ways, this is a very common way of getting them, and realize that this is simply an operation on a set of variables. It's simply an operation on a set of variables. It doesn't mean that once you do the transformation, that these components will actually mean something substantively. That's the first thing to realize, is there's just a transformation. Look, like all we've done is throw down some notation and show that it's a transformation. It doesn't mean it's going to mean anything in terms of your physical variables. So if I take a set of variables x1 through x100, there's x1, x100, and then this is a covariance matrix. So I have variances along here, I have covariances along here, and I perform a principal components analysis on this, and I transform it. It doesn't necessarily mean this has any meaning, other than I've taken the information in one format, and I've converted it into another format. I've transformed the data. Now, how many components am I going to get? Well, I'm going to get as many components as there are variables, unless you're dealing with really, really weird situations where that may be a harder thing to say. But under most situations, you're simply going to get the same number of components as variables. But what you hope is going to happen, is that most of the information loads back here on the first component. This first component explains most of the variance in your original setup, right? That first component explains most of the variation in your original setup. That's what you're talking about. Most of the variation in the variables, because you're subjecting this with variables to your components analysis. So this is called a supervised this is not called a supervised learning. The supervised learning is what we've been talking about. And we've been talking about lasso regression, we've been talking about ridge, we've been talking about regression, discriminant analysis, logistic regression. Those are all considered supervised. Why? Because in discrim, let's say, x1, x2, what did supervised mean? It meant you took these variables and you used them to classify into categories. It was supervised because you had the two categories right here. When we talk about PCA, this idea is considered unsupervised. It's unsupervised because you're simply doing a transformation without identifying a response variable. Okay, you're not identifying a response variable. Now, we'll talk next time. I'm running out of time for today, but we'll talk about next time where this distinction between supervised and unsupervised is, in a sense, it's a little bit trivial when you really think about it, and I'll unpack that a little bit more next time. But next time we will get through the first part of chapter 10, which deals with principal components analysis. We'll talk more of why it's called unsupervised. We'll talk about this principal components analysis and how it's related to exploratory data analysis such. We'll get through this. It won't take us too long. I'm hoping that this takes us the first part of next week's lecture. And then we're going to get into factor analysis. Okay, so PCA is not the same as factor analysis, but we want a really solid grounding in PCA before we can understand, why factor analysis is not principal components analysis. There's going to be some huge differences between the two. Okay, so next week, finish off PCA into EFA, into exploratory factor analysis. Exploratory factor analysis is not in the book. It's not in this book. So I'm going to be writing some notes for that. It's in the Mayer book, though. So the Mayer book also has a chapter on introduction to basically psychometrics. That's a good chapter to read because we're going to get to the exploratory factor analysis, and exploratory factor analysis is often used in things like test construction and stuff like that. So having a read of those psychometric ideas to begin with is a good idea before we get into that factor analysis model. And then once we develop the factor analysis model, we're going to be exclusively into Mayer for a little while until we come back to this book where we continue in this chapter and we continue with cluster analysis, which is another unsupervised learning technique. Okay, so that's it for today, and we will see you next week.